What's up, everybody? Welcome to another video. Hope you're ready to flex those brain muscles. In this video, we're going to practice some direct proofs. We're going to use the direct proving method to prove these four statements. And this is intended to be an introductory video for those who are new to this proving method or even new to proving in general. So these are like really good beginner examples that are good for just learning how to prove, for getting a feel for it. So if you want to, you can pause the video and try some of these on your own. If you're trying to test yourself, trying to practice, I'll have timestamps in the description below. Otherwise, we're going to continue. And the first thing we're going to look at is formally, what does it mean for an integer to be even? What does it mean to be odd? Notice that all of these four statements have to do with even and odd integers. And one of the most important things for writing proofs is we really have to know the definitions for the stuff involved in the statements that we're dealing with, right? So we really want to know, what do we mean by even and what do we mean by odd? And probably when I say even, what most people think is, well, we can take it, we can divide it by 2, and we get a remainder of 0, right? The result is a whole number with no remainder. And that's perfectly fine, that works. But the way we like to think of it formally, and especially when we're writing proofs, is that it can be written as 2 times an integer. So n is even if it can be written as 2k, where k is some integer, for some integer k. And we use this z here to denote the set of integers, right? So for example, let's think about your favorite integer. Let's see, minus 12. 12 could be written as 2 times 6. And we can sort of think of this as factoring out a 2. We can always factor out a 2 from an even number, right? Awesome. So hopefully that makes sense. Let's think about odd now. Because a lot of us probably think of odd as, well, when you divide by 2, you get like a decimal, or you have a remainder of 1, that sort of thing, right? Well, how we like to define it formally, and especially the definition we use for writing proofs, is that we can write it as 2k plus 1. So that should make sense because any odd is 1 bigger than some even, and if we can write every single even number as 2k, then we should be able to express every single odd number as 2k plus 1. So this is for some integer k again. And let's think about a couple of examples. So let's see, for example, 15, that's odd. And we can write it as 2 times 7 plus 1, right? It's 1 bigger than 14. Negatives you could do as well. They're a little bit trickier. That's equal to, let's see, negative 13. That's 2 times negative 7 plus 1, right? So every single odd integer could be written as 2k plus 1. And if an integer can be written as 2k plus 1, then it's odd, right? And another way, just to point out before we continue, another way to say each of these statements is there exists an integer k such that n equals 2k, right? That's the same thing as n equals 2k for some k in the set of integers. So you may hear both of those. This is what I prefer, but it's totally fine. It's a matter of preference. So even and odd, 2k, 2k plus 1, this is what we're going to use. Really important we understand this, because again, we need to know how these things are defined if we're going to prove stuff about them, right? So let's jump into our first example. How does the direct proof method work? Well, what we do when we're direct proving, when we're using this method, is we assume that the if statement is true. And by if statement, I mean this thing here. N and m are even integers. We want to assume that's true, and we want to show that that necessarily leads to the then statement also being true, which is n plus m is even, right? And that's really the direct proof method. That's all we do. Assume that the if statement, that's sometimes called P, assume that's true and try to show that the then statement, which is sometimes called Q, we try to show that's true. So let's set up our proof here and see if we can think about this. Assume, I like to use the word suppose. We're going to suppose n and m are even integers. And let's go and write out what that means, because that's what we just talked about. What does it mean for n and m to be even integers? Well, so n equals 2 times k for some integer k. And m equals, do we want to write 2 times k here? The answer is no, we really don't, because what that is going to imply is that n and m are equal if they both equal 2k, right? So this is an important note. Your professors probably care a lot about this. If you write this, they'll probably mark off a point, right? It's typically bad practice to use the same sort of dummy variable twice like this. So we just want to use a different letter. Simple enough solution, right? So we're going to use L for sum L. But hopefully that makes sense why we don't use the same letter, because then we're sort of suggesting that n equals m, and we're not assuming what we want to assume, which is that n and m are just even integers. They could be different, they could be the same. We don't want to assume more than that. Awesome, so we have our definition written out. So this is what I like to do with a direct proof. Identify the if statement, assume that that's true. Now we want to identify the then statement and think about what we would have to show that's true. So what we want to show is n plus m is even. And what does that mean? Well, we want to show n plus m equals 2 times some integer, right? So let's think about that. We'll write it down here. I'll use want to show. This is sort of our want to show statement. N plus m equals 2 times integer, some integer, right? And I'll just keep note of that because we want to think about how can we work toward that. We always want like a direction to go, a goal. So we always want to think about the then statement and how we can use what we've assumed to get there. Well, if I want to show something about n plus m, maybe I should figure out what n plus m is, right? So based on how we've defined n and m, n plus m is what? 2k plus 2l. And so maybe written in this way will help me write it as 2 times an integer. And hopefully you can see it. I think I can if I factor out a 2 from both of these terms. They share a common factor of 2. So I can factor out a 2, and what I have is 2 times k plus l. What I've just shown in this line is that n plus m equals 2 times k plus l. And k plus l is the sum of 2 integers. So this is an integer, right? And so I'm literally done. I've just shown what I want to show. Now I just maybe need a couple of concluding sentences here, right? So maybe I just write, since k plus l is an integer, see if I can write that a little better, is an integer, n plus m is even. We can really conclude there, right? N plus m is even because we've just written it as 2 times an integer. And how much detail you want really depends on your instructor, how picky they are. I would totally accept something like this. I think this is awesome. And hopefully that makes sense for how we got that. So again, our strategy is assume the if statement, unpack what that means based on the definitions. So n equals 2k, m equals 2l. Then think about what the then statement is and what exactly we want to show. And then we try to work down and show what we want to show. So let's try this with the next example. Apply the same strategy. Identify the if statement. What is that? N is an odd integer. Okay. So what does that mean? Well, that's what we're going to assume. We're going to suppose n is odd. And what does that mean based on the definition? So n equals 2k plus 1 for some integer k. N equals 2k plus 1 for some integer k. All right, so we started off well. We identified the if statement. We made our assumption. We unpacked what that means. Now let's think about our show statement, what we want to show. And I've heard this described as no show, right? Those are like the initial steps, what we know and what we want to show, okay? So what we want to show is that 3n plus 7 is what? Is even. Which means what? We want to show that 3n plus 7, another way to think of that is 3n plus 7 equals 2 times some integer. Right? So we want to show that 3n plus 7 equals 2 times some integer. How could we do that based on what we know? Well, we know that n equals 2k plus 1. So what is 3n plus 7 then? Let's think about what that is. Then 3n plus 7 is, well, 3 times 2k plus 1. And then what do we have at the end? A plus 7, right? So I've just replaced what n is in terms of k. Now let's continue this. 3n plus 7, what does this equal? Well, we can maybe distribute this 3. Maybe this will help. 3 times 2k, that's 6k, plus what? 3 plus 7. And now maybe we just combine some like terms. 3n plus 7 equals 6k, and we can combine the plus 3 and plus 7 to be plus 10. Okay, so now let's stop here because we're forgetting to think about what exactly it is we want to show. So let's remind ourselves of this. We want to show that 3n plus 7 equals 2 times an integer. Okay, so we have 3n plus 7 written in this way, 6k plus 10. Can we write this as 2 times an integer? I think we can. I think we can factor out a 2 at this point, because they both share a common factor of 2. And so I can factor out a 2. And so now what I can say is, well, 3k plus 5, that's some integer times 3 plus 5, right? That has to be an integer. And since that's the case, 3n plus 7 equals 2 times an integer. So that's it. 3n plus 7 is even. So we need maybe a couple of concluding sentences, maybe 1 or 2, like since 3k plus 5 is an integer, since this belongs to the set of integers, 3n plus 7 is even. So we're noticing a common pattern when we're trying to show something is usually we like come up with some kind of equation, we do some algebra, we simplify, we manipulate, and we try to factor out a 2, right? And that's going to be a pretty common theme whenever you're trying to show something's even. You're just in the end trying to factor out a 2 and write 2 times something. And once you get more practice, this will become just super easy. Hopefully this makes sense. We used our same look at the if statement, make our assumption, unpack that definition, look at our then statement, write out what we want to show, and use that to guide what we're doing here, right? Awesome. All right, we're halfway through. Let's try the next one. Hopefully this is helping. If x is an even integer, okay, so now that's our assumption, that x is even. So let's go and write out what that means. We're going to suppose x is an even integer. Okay, and then what that means is, well, then x equals 2k for some integer k, right? So we're going to unpack our definition here for some integer k. All right, now what are we trying to show here? Well, that 5x minus 3 is an odd integer. Okay, so that's what we're trying to show. So what does that mean? Let's write it down here. We want to show that 5x minus 3 is odd, so I'm going to go ahead and write out that 5x minus 3, I'm going to use the definition of odd. I'm going to go ahead and write that out, is 2 times some integer, all right here, integer, and you could always use a symbol here. You could write q or something, right? I just like writing some integer in there, plus 1, right? That's what it means to be odd. We want to show that it's 2 times an integer plus 1. So let's see if we can get that. What we have so far is that x is even, so x equals 2k. So we can use a similar strategy. We can say, well, what is 5x minus 3 then? So 5x minus 3, and remember last time we wrote x, we rewrote x in terms of k. Let's do that again. Let's replace x with 2k. Well, then 5x minus 3 is 5 times 2k minus 3. So what does our next line give us? 5x minus 3 is equal to, let's see, 10 times k minus 3. All right, let's think about what we're trying to show again, because I have no real like terms to combine, no more like distributing to do or anything like that. We want to show that 5x minus 3 equals 2 times an integer plus 1. How can I do that? So this is when we got to be a little bit clever, right? Because I really want to factor out a 2 here, have some stuff left in the parentheses, and have a plus 1 left on the outside. Let's see if I can force a plus 1. Let's start with that. 10k, what would I have to do to write a plus 1 here, but keep the value the same? I would have to change this to a minus 4. So I'm rewriting minus 3 as minus 4 plus 1. Hopefully that makes sense, and hopefully you see why those are still equivalent, why I'm allowed to do this. So this is a classic example. We do this a lot in proofs. Is when we add 0 in a clever way, right? Because we just added 1 and subtracted 1. So what does this give us? Well, now we can factor out a 2 from the first two terms, and we're left with 5k minus 2. And we do have a plus 1 left on the outside here. And 5k minus 2 is an integer. So what we've done is we've written 5x minus 3 as 2 times an integer plus 1. Hopefully this makes sense. We still need a couple of concluding sentences here. This time I'll leave you to write those. Hopefully you got the hang of that by now, right? Since this is an integer, we've just shown that 5x minus 3 is odd. And let's move on to the very last example. Hopefully this is helping. Let's see, if a and c are odd integers, then a times b plus b times c is even for every integer b. Interesting. Okay, so now we got to unpack some stuff. We're going to suppose that we have these two odd integers, a and c. Suppose a and c are odd integers. And we're going to think about what that means. Suppose a and c are odd integers. Then what? Well, then a equals 2k plus 1 for some integer k. And what else? And c equals, remember, we don't want to use the same letter, so I'm going to use 2l plus 1 for some integer l. Awesome. All right, I think this is what we have from unpacking that if statement, from assuming it's true. Let's think about what we want to show. We want to show something about a times b plus b times c for every integer b. Okay, let's think about what that means. So we want to show a times b plus b times c equals 2 times an integer. All right, let's write that down here. I want to show statement. Want to show a times b plus b times c equals 2 times some integer. This time I'll call it p. I'll give it a name. Right, 2 times some integer. Since we want to show this for every integer b, at this point in the proof, what I think we need to do is let b be some arbitrary integer, right? Because we're about to use b, and before you just introduce stuff in a proof, you typically want to, introduce it, right, in a formal way. Let b be an integer, rather than just going straight to, well, then ab and bc is this. We want to say, what is this b thing? So let b be an integer, and now we can think about what is a times b plus b times c. All right, so what is this? Well, this is a times, let's see, what is a? 2k plus 1. Let's replace a and c with what they are in terms of k and l, right? So kind of consistent with what we've been doing. We'll leave b alone because all we know about b is that it's an integer, but we know a and c are odd. Let's use that. So 2k plus 1 times what? B, okay, plus b times 2l plus 1. All right, and what we're trying to show is that this is all equal to 2 times an integer. How are we going to show that? Well, I see we have a common term of b, so there's a couple different ways to do this. The rest really is all algebra. There's 2 different ways to do it though, right? So first of all, if you can see this as 2 terms, 1, 2, separated by this plus, and you can think about factoring this b out in front of both the terms, then you can go straight to that step, right? If that's weird and you don't see what I'm talking about, then you can distribute the b. You're going to have a b in all 4 terms and then factor it out at the end. Either way you do it, what you're going to be left with is this. This b is going to come out here in front, and everything else is going to be in parentheses. 2k plus 1 plus 2l plus 1. And now look what's about to happen, right? Because the b is still chilling out in front. But what we have here is 2k plus 2l plus 2. I can definitely take out a factor of 2 from this, right? I can definitely take out a factor of 2. Really, since I want to be 2 times an integer, I think I should probably put the b back in, right? But what I'm going to end up with here is if I factor out a 2, I have 2b out here, k plus l plus 1. And I can put the b back in if I want, because I really want to be explicit about, hey, this is 2 times something. So it turns out that I can put the b back in. bk plus bl plus b. And I'm sure there were different ways to do this. There may have even been an easier way. This is just the way I thought of. But eventually what I got to is that, hey, ab plus bc is in fact equal to 2 times bk plus bl plus b. This is a bunch of integers being multiplied and added together and stuff, so we know it's an integer, and so we can make our couple of sentences concluding this proof and saying, hey, since this is an integer, we've just shown that a times b plus b times c is 2 times an integer, and therefore it's even. All right, hopefully this example made sense. Hopefully this video helped. If you have any questions, leave them below in the comments. Make sure to like the video, subscribe. Most importantly, keep flexing those brain muscles, and I'll see y'all next time.